Hello everyone and welcome to the first video in Paradigm on solving math problems in competition math. We'll be focusing primarily on like AMC 12 or AMY level. Today we'll start simple, start with our first ever AMC 12 2000, or first ever at least on the Art of Problem Solving website. And we'll just start with the first 10 problems or so. And I'll be working at an intermediary to an advanced rate, so if you have prior knowledge in math competitions, you should be fine. As long as you have some experience, you can keep up. These are relatively easy problems as well, so you should just be fine. Alright, problem 1. In the year 2001, the United States will host the International Mathematical Olympiad. Let I, M, and O be distinct positive integers such that the product I, M, O is 2001. What is the largest possible value of I plus M plus O? Okay, well we can jump right into this and solve it, but let's do this a little conceptually first. 25 is 5 times 5, right? The sum is 10. However, 10 is not that large. 25 times 1, however, is 26. This is way larger. How? Because larger factors scale into the sum, or weigh into the sum a lot more than these even factors. So we want to have a really unbalanced factor that's really high. So if you look at this 2001, we notice that it's divisible by 3, because the sum of the digits are divisible by 3. You can say 2001 equals 667 times 3. And we also have this invisible 1 factor. This sums up to 671. Now how do you know that's our answer, not something else? Well, we're looking for the largest possible value. Are these larger than 671? No. Is 671 possible? Yes. So that's our answer. Very simple problem. Okay, problem 2. It's a problem of exponents. Okay, so if we were to rewrite this, let's look at the definition of exponent first. So 2000 to 2000. This is just repeated multiplication. We're multiplying 2000 times, right? It's just 2000 of these. So if I were to add another 2000 to it, then I would have 2001 of these, which is the same thing as 2000 to the 2001st power. Very simple problem. Okay, problem 3. Each day, Jenny ate 20% of the jelly beans that were in her jar at the beginning of each day. At the end of the second day, 32 remained. How many jelly beans were in the jar originally? Okay, so here we have an end condition, and we want to find the beginning condition, our starting conditions. So let's declare a variable for our starting conditions to make things way easier. So we have, say, x on day 1, right? Or day 0. After 1 day, only 80% of our jelly beans remain, so only 4/5 of our original remained. On day 2, 4/5 of day 1, right? We don't have 4/5 of this. 4/5 of day 1 remained. So if we multiply 4/5 to this, we have 16/25. And this is equal to 32. Very quickly, we can just solve for x, divide both sides by 16, multiply by 25, this is just 2, so we have x equals 50. Right. Okay. Question 4. The Fibonacci sequence, blah blah blah, starts with 2 ones, and each term afterwards is the sum of its 2 predecessors. Which one of the 10 digits is the last to appear in the units position of a number in the Fibonacci sequence? Wow, there are no commas there except this one. What this is saying is, which one of these digits, like 0, 1, 2, 3, 4, yada yada, is the last to appear and the rightmost digit? Now notice, it says units digit. Do we care about the tens digit? Not at all. Do we care about the hundreds digit? Not at all. So let's just ignore those. Because the tens digit, when we sum them, it can't influence our units digit whatsoever. What we're doing is called modular arithmetic. We're doing mod 10 of each number. It's okay if you don't know what that is, but it's just a topic to have in mind if you're interested. Okay, so let's do this. We have 1, 1, 2, 3, 5, 8. And 5 plus 8 is 13, but we don't care about the tens, so it's just 3. 8 plus 3, 11, so just 1. 3 plus 1, 4. 5, 9, 4, 3, 7, 0, 7, yada yada. So let's just look at these real quick. We have a 1, we have a 2, we have a 3, a 4, 5. We don't have a 6, but we have a 7, 8, and 9, and 0. So we have every single digit except for 6. So our final answer is 6. It will be the last to appear. And yes, it does appear. So we can continue this. 7, 4, 7 plus 1 is 1, 5, and here we have 6. Okay. Problem 5. If the absolute value of x minus 2 is p, where x is less than 2, then x minus p equals... Okay, so first things first. If x is less than 2, then this will always be negative, right? Because we're subtracting a number bigger than 2, or bigger than x from x. So if this is always negative, then the absolute value is needed for this to be positive. So we can say x minus 2 equals negative p. If that didn't make sense, here we have x minus 2 equals p. That means this x minus 2 right here, this could equal p. The equation still holds. But this could also equal negative p. This equation holds because the absolute value of negative p is p. We already know that this is negative, so you can say for certainty that this is negative p, right? Positive p is not a negative number. So looking at that, we're looking for this x minus p. So we can add 2 to both sides and subtract p from both sides. And we can see our answer is just c if we rewrite this. Alright. Question 6. Oops. Let me just get rid of this real quick. I don't know why this is here. Okay. Question 6. Two different prime numbers between 4 and 18 are chosen. When their sum is subtracted from the product, which of the following numbers can be attained? Okay, so let's list all the primes between 4 and 18. 5, 7, 11, 13, and 17. And let's just call these two primes that are chosen, let's say a and b. So we're saying ab minus a plus b equals this x, and x could be any of these. So I'll just expand this real quick. And here we have something called Simon's favorite factoring trick. So this works when we have a quadratic or some anything in this form. Right, all of you guys know this is the quadratic form, the factored form. And we want to see this when x equals 1. We can see this expands to 1 minus p minus q plus pq. I know this is a very random concept, I guess. If you've never seen this, you might say, why? This is so random. However, this comes up a lot in competition, surprisingly. And one example is right here. This is identical to this. We just need to add the 1, right? So if I move this over, let's try this. A b minus b plus 1 is x plus 1. And we have 1 minus a, 1 minus b equals x plus 1. Wow. This is a lot easier to work with. And also notice that all these primes are bigger than 1. So this is negative, this is negative. But 2 negatives is, yes, a positive. So we can just a minus 1. I'm multiplying both of these by negative 1 so they cancel out. Okay, let's get rid of this. We don't need this anymore. We have two numbers, a minus 1, b minus 1. When they multiply, is equal to one of these plus 1. So a minus 1, b minus 1 could all equal 4, 6, 10, 12, or 16. That's just all of these subtracted by 1. And, okay. If x plus 1 is equal to one of these, or x is one of these, x plus 1 could either equal 23, 61, 120, 195, or 232. We can really quickly see that 10 times 12 is 120, so that's our answer. And of course, these are all even numbers. These can absolutely not be answers. 232 is way too big. 16 squared is 256, so yeah, you already know. But if you just want to work it out, I guess you can do that. Alright, question 7. How many positive integers b have the property that log b 729 is a positive integer? Alright, so log, recall, if we have like 2 to the 8th, or base 2, 8, that means this is equal to 3 because 2 cubed is 8. So right in the same way, we have log b729 is a whole number, let's say n. So this 2 goes out of the base, so we have b to this n power equals 729. Okay, so how many values of b are possible? Okay, well, we noticed that 729 is 3 times 3 times 3 times 3 times 3 times 3, 3 to the 6. I don't know, it was probably like not needed for me to say 3 times 3 6 times, but whatever. So how many ways are there to get 3 to the 6? Well, we can say b is 3, so there you go, that's one way. Is there another way? Yeah, 9 squared. Is there another way? Yeah. We have, or not 9 squared, not cubed. 27 squared. I'm wondering, how are you getting these? Well, 3 6 is the same thing as 3 squared cubed. Or 3 cubed squared. Right? So this is just 9 cubed and 27 to the 6. Alright? What about this 729? This could also equal 729 to the first. So how many values do we have? 4. That's our answer. Okay. Question 8. Figures 0, 1, 2, 3 consist of 1, 5, 13, and 25 non-overlapping unit squares, respectively. If the pattern were continued, how many non-overlapping unit squares would be in figure 100? Wow, these are some large answer choices. Okay, so how do we approach this? Well, obviously these are very symmetrical, and also they're very geometrical. Let's try to look for a pattern. If this is figure 0 is basically right here, and we're adding this 4 to the outside. So this is figure 1. Figure 1 is basically right here, and we're adding these, 8 to the outside. Right, so this pattern continues. We're basically adding 1 to this outside each time. Okay, well, how many are we adding? Notice that all these are symmetrical in 4 directions, right? So here we have 1. Here we're adding 1 square 4 times, right? So 1 plus 4. Of our original, which is 1 plus 4, we're adding 1, 2 squares, 8, or 4 times again, right? That's right here, right here, right here. We're adding 8. And here, let me get rid of these. Shit, I've been writing on the wrong layer this whole time. Okay, I'm just getting 1, 4, 1 plus 4. 1 plus 4 plus 8. Here we have 1, 2, 3. We're adding 3 4 times again. So that is 1 plus 4 plus 8 plus 12. Yeah, because 3 times 4. The next layer will be adding 1, 2, 3, 4 squares 4 times. We have plus 16. And so if figure 3 was just as 12, we can say figure n is 1 plus 4 plus 8 plus 12, and then 4n times, right? Because if n was 3, this would be 12. That makes sense. How do we know what this is? Well, we can say this is 1 plus 4, 1 plus 2 plus 3, blah blah blah, up to n. And this is just the sum of numbers. If you don't know what the formula is, it is very simply n plus 1 over 2. If you want to derive this, it's very easy. You can do that as an exercise or look it up. So you can say 1 plus 4 is 100, 101 over 2, since we're going up to 100. This cancels out, and we have 1 plus 200 times 101. This is obviously 1 plus 20200, so we have 20201, so we have C. Okay, question 9. Mrs. Walter gave an exam in mathematics in a mathematics class of 5 students. She entered her scores in random order into a spreadsheet, which she recalculated the class average after each score was entered. Mrs. Walter noticed that after each score was entered, the average was always an integer. The scores, in ascending order, are 71, 76, 80, 82, and 91. What was the last score Mrs. Walter entered? Wow, this problem is not very approachable. So we're saying, for example, let's just go in this order. 71, that's an integer. After her next score, this is also an integer. Well, that's not an integer, so we know this is false, but that's the idea. Okay, so when we want to approach this problem, let's think about it logistically. Sum of the first 2 must be divisible by 2. Sum of the first 3 must be divisible by 3. Same thing with 4 and 5, right? So if the sum of the first 2 are divisible by 2, they're either both even or both odd. Let's say A, B, C, D, E are these 5 numbers. So we have A plus B over 2, A plus B plus C over 3. So these must be divisible by 3. Plus C plus D over 4. These must be divisible by 4. And obviously the last one is divisible by 5. Okay, so first things first, we have 1, 2 odd numbers and 3 even numbers, which means, pigeonhole principle, we must have an odd number. If we have one odd number only, this will fail. This will fail. This will it might work, but it'll probably fail too. So we must have 2 odd numbers, which means they can be introduced here. Can they be introduced here? Yes. Can they be introduced here? Yes. So we don't know yet. Even numbers can be introduced anywhere as well. So let's just try it. There is a faster way to do this with mods, but that's not very approachable at a lower level, so let's just try this. If we want this to be divisible by 3, we want all of these numbers mod 3 to equal 0. So let's look at these. 71 mod 3 is 2, right? 76 mod 3 is 1, 80 mod 3 is 2, 82 mod 3 is 1, 91 mod 3 is 1. We can very quickly see that the only way to get this mod 3 to 0 is with this 1, 1, 1. 2 plus 2 plus anything is not going to work. 2 plus 1 plus 1, that's 4, that's not mod 3. If you don't know what I'm talking about, I'm saying that when we divide all these numbers by 3, there's going to be a remainder. That remainder is either 2 or 1. To make the number divisible by 3, we want the remainders to add up to 3. Let's recall that, like say 76 is 25 remainder of 1. If we add this, this, and this together, we have, what is this? 27 remainder 1 and 30 remainder 1. Which is the same thing as all these added, and 1/3 plus 1/3 plus 1/3, which is just 1. So these are divisible by 3, because 1 plus 1 plus 1 is divisible by 3. If all that just went over your head, it's okay, just look up modular arithmetic and you'll get the basic sense of it. But I'm already assuming you know a little bit. So if these numbers are 76, 82, and 91, not in any particular order, well, 91 is odd. That means these must be 76 and 82. Right? Because an odd number plus an even number cannot be even, or cannot be integer. Here we have an odd, so we must have this other odd number, and we divide by 4. There's 70, 71, 76, 82, and 91. So our last number must be 80. So our answer is C. Yeah, that was a lot tougher than the previous problems we had, but it's okay. We're getting to the harder problems. Okay, problem 10. The point P, 1, 2, 3 is reflected on the xy plane, and its image Q is rotated 180 degrees about the x-axis to produce R, and finally R is translated 5 units in the positive y direction to produce S. What are the coordinates of S? Okay, so let's say P is at 1, 2, 3. If we draw a really horrible coordinate plane, let's call this positive x, positive y, positive z. We go 1 in the x, so that's like right here, 2 in the y, so right here, and 3 in the z, so here. So it'd be like right there, right? If we rotate this 180 degrees around the x-axis, we're doing this, right? If we were to think of this like L leg, we're rotating this L leg 180 degrees, so it looks like this. Well, this y distance does not change, it's going to be like this, in the opposite direction, right? The c distance is not going to change, it will be like this, in the opposite direction. Our x is still the same, because we're rotating around the x-axis. So if we draw this again, like right here, we'll have our same x, our y goes negative, and our z goes negative. And R is translated 5 units in the positive y direction. So we add 5 to our y, show it here like this, or just add it here. And our final answer is not here, right? Oh, my bad. Let's see, did I mess up somewhere? Oh, it says reflected in the xy plane. I completely skipped that step. My bad. So, in actuality, we have, if it's reflected in the xy plane, right here, that's our xy plane, our z value becomes negative. So in reality, this would actually be right here, and we still translate it, so it would be 1, 3, 3. Alright, sorry for making this more confusing. Messed up in the last question. I know it's incorrigible. However, same answer. None of these rely on this z variable, so we can just flip it. Doesn't matter. But yeah, hope you guys enjoyed this little AMC recap of our first 10 AMC 12 questions in 2000. We'll be covering 11 through 20 in the next video. And yeah, hope you guys like this. Remember to subscribe to our channel, help us grow, and I'll see you guys in our next recap.